Okay, good morning, Thermo students. It is Wednesday, 15th. Yesterday was Bastille Day. But nobody has shown up yet. Our topics are on the board. We're going to study a diesel cycle in English units. Then I want to have a very special review. Did you know next week is our last week? And I think your final is a week from today. But I'm just going to wait for some of my wonderful students to show up. But I could draw that. I could draw that diesel cycle. The one I wanted was 10-122E. Okay, let me write that down for you. This says, oh, no. No. It's air. We don't have any vapor dome with air. It's a diesel cycle. We're talking about air. So it says it starts off with 520 Rankine. Okay, 520 Rankine. Let me write that. $520 Rankine. It starts off there at 900, no, they don't tell you the pressure. We don't know. They just tell you the maximum temperature. Okay. Well, we know the diesel cycle has an adiabat like so, and then an isobar. Here, let's put this state one more down here. There's state one down there. And then there's the power stroke. Okay, that's your PV diagram. Now they said the maximum temperature is 3200 Rankine. Good morning, Stuart. How the heck are you?
Doing pretty good.
That's good. Stuart, we only have 1 week of school left. Did you know that?
I did.
Yeah, next week's the last week. Now that there is 3200. That's your maximum temperature. And what we did, here, let me get that. We did a diesel cycle last time on Monday. Today's Wednesday, but it was in SI. We're going to do one in English. Our first topic today is a diesel cycle in English units. We're dealing with air, and I thought we'd go through 10.122e. I think you need practice using the English units. They're kind of tricky. And so I'm looking at this 122e here. It has a compression ratio of 20. They don't tell you a whole lot. But they do tell you the maximum pressure is 920. So this, we do know this right here. It's 920 PSI. We do know that the maximum, or the, maximum pressure, 920. We know that. And the compression ratio is 20. Yeah. We'll write that down here someplace. I usually use the symbol R for the compression ratio. I think that's all we know. Well, we'll get around to all the rest of it here in a minute. Let me see who we got on board here. We have, we've got Spencer and Stuart. Good going, my faithful ones. They're here, eager to learn, and that's what I like. Before we launch into this exciting diesel cycle, do either one of you guys have a question for me? Comment or question? Spencer, you sent me an email and I've been too lazy to look at it, but I will, I promise, I will look at it. Well, okay, if you do have a question, that's what I'm here for. So let me fill out this table now. I wonder if I'm writing big enough to where you guys can see that. Probably not. Probably not. And last time I talked about when I grade your papers, your tests, and your homework, there's a little box for the instructor to write in the instructor comments. And I've been faithfully writing in comments on things that you could do to improve on your homework and exams. And some of you told me last time that you weren't receiving that. Well, I talked to my IT person, my daughter, and she told me to keep writing those comments to help the students, and that they're there, but maybe you just don't know how to access them. Until I learn more, I'll just keep writing that stuff. Like how you missed a problem, you forgot to do this or that. And by the way, that exam we had, I posted the key. It's on content. So you go to content, and the key to that exam 3 is on there. And there should be a key to all of your exams on content. If there's not, you let me know, okay? Okay, well, let's see who's on board now. Let's see here. Oh, we got a good crowd. We have Cameron now and Parker. Yeah, excellent. It's easy to teach a class when you've got such good students. Okay, well, let's let's go ahead and do this diesel cycle. It's a real cycle. They have diesel engines in the real world. Go take a drive on the freeway sometime. And when one of those big trucks goes by, that's a diesel engine. All right, now let's fill in some boxes. It says there that the pressure, well, they don't give you the pressure at state 1. Too bad, we don't know. But they do give you the pressure at 2 and 3, so let's write that in. That's 920. These are PSI. We're doing English. But when you do a thermodynamics problem, you have to decide, is it English? Actually, it's called the British Engineering System of Units. Or is it SI, which we used to call the metric system? And you don't want to mix them. You want to, whatever the system is, you stay in that system. I've had students that think that what you're supposed to do is convert, like if they have an English problem, they'll convert everything to metric, solve it in metric, and then when they get all through, they'll convert it back to English. Don't do that. If you're in English, do everything in English. If you're in metric, do everything in metric. Don't be converting back and forth. That's crazy. Okay, well, let's see. Oh, we also know the pressure at 3 is 920. Maybe there's something I'm missing. Let me read the problem again. It says here, maximum pressure, maximum temperature is 3,200. Well, let's write that in there. That's temperature at state 3, 3,200 Rankine. Okay. Well, now that we know P3 and T3, we can go P3V3 is equal to RT3. All right. I want to see if any of you guys know how to do that. I mean, we know what R is. Here, I'll write it for you. It's 5334 foot-pounds force per pound mass Rankine. That's what it is. T3, it's sitting right there. It's 3,200 Rankine. P3 is sitting right there. It's 920 PSI. Look, you know this. You know this. You know this. You should be able to get that. I'm going to shut up now for a minute and a half. And we're going to see if you can do it. You're going to find this V3 for me. On your mark, get set, go. See if you can do it. Okay, a minute and a half is up. Let's go to one of my faithful and excellent students. Hey, we got Roxana with us too. Good morning. Stuart, I'm always picking on Stuart. Do you have that little V3 for me yet, Stuart?
I got 1.288.
That's what I got. 1.288. Now what those are is cubic feet per pound mass. So we're doing great. That's the specific volume at 3, right? Yeah. Okay. Well, I just got a bad feeling maybe I'm missing something. Let me read this again here. Maybe I'm missing something.
You can figure out T1 from what they give you.
Oh, thank you. Was that my friend Spencer?
Yes, sir.
Spencer, good going, proud of you. T1 is 520. So let's put that in. That helps. But we don't know P1. And we don't know V1. Too bad. But I mean, every little bit helps. Let me read this again here. Okay. Well, I don't see anything obvious. But that was a good suggestion, Spencer. Anybody else got any bright ideas? Do you remember, here, let me make some room here. Do you remember a diesel cycle has two, the ideal diesel cycle has two isentropes. I hope you remember what an isentrope is. Here, I'll write it for you. Isentrope. What that is when delta S is 0. And if you have an ideal gas like air, then you can do this here. And let's see. Maybe this will work. T2 over T1 is equal to V1 over V2 to the K minus 1. Actually, there's another part to this here. Let me write the whole thing for you. It goes P2 over P1, K minus 1 over K equals V1. See, it switches on the little V's. We derived that formula one day. I don't know when, a week or two ago. But do we know T1? Well, yeah. And do we know V1 over V2? Well, it's a little bit subtle, but yeah, we know that. They said the compression ratio, see, the fancy name is compression ratio. That's what that stands for. They said it was 20, I believe. I think that's what they said. Let me double check here. I don't want to lie to you. Says here compression ratio is 20. It's 20. And you know what that is? That's V1 over V2. See, V1's here. V2's there. So we know what that is. Oh, we can do this. Look here. Let's put our numbers in. T2 over T1 is equal to 20 to the 1.4 minus 1. Okay. Can you read my writing? Can you read my writing? T2 over 520. Yeah, you can read my writing. Go for it. Let's find out what T2 is. Here we go. Well, I did that. I get a humongous number. But I can't help it. Well, it gets hot. This is a diesel engine, and they do get hot. I'm getting 1723.5 Rankine. Pretty hot. Sounds hot to me. Wonder if that's what I got. Yeah, yeah, we're doing good. Well, so what? Aha, looky here. P2 V2 equals RT2. Let's do that. Any question on that so far? All right. If you're happy, I'm happy. Now we're going to do P2 little v2 equals RT2. Now, if you can just remember that you have to put a 144 in there. If you don't put that 144 in there, it's no good. Okay, I'm going to do that. And I want you to do it. And I'm going to call on one of my wonderful students here in just a minute. You have a minute and a half. Find that V2, go for it. Well, I got an answer. It might be right. Roxana, do you have that V2 yet?
I do, but I think the answer is a little bit too high. What was R again?
Here, let me write R again for Roxana. And Roxana, take your time. I'll pick on somebody else here. Let's see. Cameron, do you have that little V2 yet? I've got an answer. I'm not sure it's right.
Is it 0.6939?
That's what I got. Good going. Do I need to write that out for anybody? I didn't hear anybody say, Mr. Griffin, write it out. So we're going to move on. Okay. Now, if the compression ratio is 20, here's how it works, guys. V2 over V1 is 20. They call that the compression ratio. Well, we got V2. Look, Cameron and I both got the same thing, so I bet it's right. And now we can solve for V1. See there? Go for it. V1. I'm going to do it. I want you to do it. And I will pick on my friend Parker. Parker, can you get V1 for me?
Is it 0.035?
Yeah, that's pretty good. I like 3 digits, Parker. You did fine, but I would be more happy if you went 0.0347. So make me happy. See, that gives me 3 significant digits. .035 is really only 2 significant digits. Do all your work with 3 significant digits. Now look at here. P1 V1 is equal to RT1. All right. Guys, P1 little v1 is equal to R little t1. No, not, that's a big T1, isn't it? There is no such thing as a little t when it comes to temperature, and pressure is always a big P. Okay, we're going to solve for the pressure now. I'm going to do it, and I want you to do it. And I'll pick on one of you guys in a minute. Find the pressure at state 1. The compression ratio was 20. We did that. Okay, right now, I'm finding P1 because I know V1, I know R, and I know T1. I should be able to get P1. Here goes. Don't forget, there's a 144. You got to put that 144 in there or it doesn't work too good. Well, I got an answer. We're trying to find P1. I didn't get this. I didn't get the right answer for that there. I did something wrong. I wonder what I did wrong. I think I made a mistake here, guys.
Looking at the graph, it feels like V1 should be a lot larger.
Yeah. Something bad happened. V1 should be bigger than V2, right?
Significantly.
So what did I do? Divide instead of multiply?
I believe you wrote V2 over V1 was equal to 20. I think it should be V1 over V2 equals 20.
So proud of you. You're absolutely. Now who was that just spoke up?
That was Stuart.
Who was it that just spoke up before Stuart?
Spencer.
A couple of thank you points up there in the corner. Here's what we want to do. We want to go V1 over V2 is 20. I guess I did it the wrong way, didn't I? And see, we know V2. I think I divided by 20. But we're going to multiply by 20 this time. And we're going to be fine. Did you get 13.88? Now we have V1 and you have the correct V1. That's going to help. And now we can get the correct P1 from the ideal gas law. So here goes. I'm going to do it now. Okay, I've got, well, this is kind of weird. This is kind of weird. Did I do something wrong? What did you guys get for this pressure here?
I got 13.88.
I did too. I get 13.88. The numbers came out the same, didn't they? That's
I
kind of
also
weird.
worked it with the ratios. The
Yeah.
T2 over T1 equals P2 over P1 to the K minus 1 over K, and got the same thing. So I think
Yeah.
it's right.
I do think it's right. I don't care whether you work it this way or work it this way. I think everything's okay. We just have to learn to have faith in our work. Okay, now here's one of the dirty little secrets about the diesel cycle. This is an isochore going from 4 to 1. So the specific volume at 4 is 13.88 because 1 and 4 have to have the same specific volume. But I don't know the temperature at 4. And I don't know the pressure at 4. Anybody got any bright ideas about finding T4 or P4?
The ratios that we used for T1, T2, V1, T2, V1, V2, can those be applied for 3 and 4?
Yeah, because it's an what's the word? Isentrope. That's exactly right. So let's do that. Here goes. Now what we're doing is we're going from 3 to 4. So you go T4 over T3 is equal to P4 over P3 is equal to V3 over V4. Wait a minute, this has to have a K minus 1 over K. This has to have a, is that right? Did I write that down right? I got a bad feeling about that. I hope you wrote that equation down someplace. I did. And I've got it here. Yeah, that's right. That's right. Okay, now let's circle the stuff we know. Now we know T3. Yeah. We don't know P3. Yeah, we do. Yeah, we know what P3 is. Yeah. But we don't know T4. We don't know P4. We know what K is. You could circle all those. Here's the beautiful thing, 3 and 4. No, yeah, we know those. See those? We know 3 and we know 4. Look, V3, V4. We can do that. So here goes. T4 over T3 is 3200, right? Is it V3 is 1.288. Is this showing up on your board? Maybe. Yeah, I think so. Divided by V4, which is 13.88 to the 1.4 minus 1. We can do it. All right, here goes. I'm going to find T4 now. Well, I got T4. But I want to see what you guys got. Let me go to my friend Parker. Parker, do you have T4 from this equation yet?
Not yet.
Take your time. I need to warn you guys, this equation, it only works if you have an isentropic process with an ideal gas. It's got to be an ideal gas or it will not work. But we have an ideal gas. We have air. We can treat air at these temperatures as an ideal gas. And going from 3 to 4 is an isentropic. It's a reversible adiabatic. We're doing the ideal diesel cycle. Well, I got an answer. Parker, do you have it yet?
I got 1236.4.
That's what I got. 1236.4. We did great. Oh, well, now look at here. P4V4 is equal to RT4. After a while, this stuff gets boring, you know, it's just the same old boring stuff over and over again. But my thinking is boring is good. If you're just utterly bored by the repetition of this stuff over and over, that means you've got it. You're bored, you've got it. P4 V4 equals RT4. Now we're going to solve for P4 because we know the rest of the stuff. What does it mean in this class when you circle things like this? Do you know what that means in my class when I circle stuff? Do you? I'll call on one of my wonderful students here. Stuart, I'm always picking on you. What does it mean, Stuart, when I circle stuff?
It means we already know it.
We already know it. So you can solve for that. I'm going to do it. You're probably done already, but I haven't done it yet, so I'm doing it now. Push the wrong button. I have to start over again. Don't forget that 144 or else it doesn't work. Hey, I got an answer. I got an answer for the pressure at state 4. Pick on Cameron. Cameron!
I got
you?
32.99.
That's what I got. I'm just going to round it off, Cameron. I'm going to call it 33.0 PSI. That gives me 3 significant digits. See, that 0 after the decimal point is significant. If it's, well, we don't need to explain significant digits to you guys. You've had enough science classes. You know that 0 is significant. Okay, well, let's get our delta U's and Q's. Wait a minute, there's 2 of these Q's that are 0. And that's 2 adiabats. You see, 3 to 4 is really an adiabat. Did you know that? It's an adiabat. The Q is 0 from 3 to 4. And from 1 to 2, it's an adiabat, so that's 0. Now, one of these W's is 0, which we'll go to my friend Spencer. Spencer, one of these little W's is a 0. Which one is it?
The last row, 4 to 1.
Yes, it's a 0. Good going, Spencer. Now, these are all BTUs per pound mass. All of these are, because see, we're in English. I don't know if I ever told you what a BTU was. If I did, I'll tell you again. It won't hurt anything. What's a BTU? Well, if you take 1 pound of water, 1 pound mass of water, and you transfer heat energy to it, and the temperature goes up 1 degree Fahrenheit, which is an increase of 1 degree Rankine. An increase in Fahrenheit is equal to the same increase in Rankine. You know what? The heat energy required to do that is by definition a BTU. Now you know what a BTU is. It's the amount of heat energy necessary to raise 1 pound mass of water at standard conditions, 1 degree Fahrenheit. There's something similar to that. While we're talking about that, there's something called a calorie. I know you've heard of calories. What a calorie is the amount of heat transfer necessary to raise 1 gram of water 1 degree Celsius. I bet you've heard that. I bet you've heard that. Now they also have something called a kilocalorie. It's a K. See, that's a little c. The other name for a kilocalorie is capital C. And you know what that is? That's the amount of heat transfer necessary to raise 1 kilogram of water 1 degree Celsius or Kelvin. It would increase 1 degree Kelvin, same as an increase of 1 degree Celsius. Now this is a capital C. This is a little c. This is the calorie that's on your box of Wheaties or your candy bar. Go to the grocery store, look at anything, and it'll say so many calories. Okay? Or you go to the restaurants nowadays, and they have these dinners, and they'll tell you this fish dinner with all the stuff on it, the baked potato and everything, 1,200 calories. Well, those are big C's. Those are really kilocalories. I bet you knew all that stuff, but maybe not. Didn't hurt any to go through that. Hey, let's get these delta U's. Here we go. We're going to get all the. Any questions on any of that? Well, see, when you don't ask me any questions, it's one of two things. One, you understand it perfectly. You don't need to ask a question because you got it. Two, you don't know enough to ask a question. It's so far above your head that you have no idea what's going on. I hope it's not that. All right, well, let's do the delta U's. Now, here's how you do the delta U's. Since it's air, which is an ideal gas, you can do that. Be careful with this equation. It only works for ideal gases. Okay, now we're in English units. So this here, it's not 0.171 kilojoules per kilogram Kelvin. See, that's SI. You don't. If you're in English, you don't use SI. What this is if I remember right, strangely enough, I think it's 0.717 BTUs pound mass, Rankine. Now what, if you're gonna go say from 1 to 2, then the temperature from 1 to 2, well, that would be 1723.5 minus 520 Rankine. And that should give you your delta little u, your change in specific internal energy. All right, I'm going to do that. Here goes. Well, I got an answer. I don't know. This is what I got. I'm getting 862.9 BTUs per pound mass. I wonder if that's what I got the last time I did this. Let's see. No, that's not what I got. I did something bad happened. That's not right. I think I did something wrong. Okay, well, let me try again. That is the right number, isn't it? No. That's that. I got them backwards, guys. This is the 171, and this is the 717. Somebody could have jumped on that and gotten a nice thank you point. If you look these up in the back, that's what you'll find. Let me show you so we'll get this right. This is wrong here, fellas and ladies. That's not right. Okay. Go to the back and look up. And where do you find this stuff? Let's see. Okay. All right, I found it. This one here, I found on table F.4. Now this one here, let me tell you where that is. See, that's in the SI. So you have to go to the SI tables. Let me see if I can find that. Okay, there it is. This is found on table, see, I got them mixed up, didn't I? That's found on table A.5, table 8.5. Okay, well, great. Now we can get the right answer. So here goes. It helps to have the right numbers. I wonder if this is right. I'm getting 205.8. I wonder if that's right. Yeah, that one's a lot better. We're doing good. Okay. Anybody getting 205.8? Right here, 205.8. Can you read my writing?
Yeah, that's what I also got.
Yeah, I like to hear that. Okay, now we're going to get the delta U here from 2 to 3. All right. Well, you know, it'll be the same deal. It's just you got to put in the different temperatures here. Let's see. That'd be 3,200 minus 1723.5. Okay, go ahead and get that one. Well, I got an answer. I don't know if it's right or not. I'm getting 252.5. 252.5. Yeah, I think that's right. Okay, this is just tedious and boring, but we can do it. Now we're going to get the 3 to 4. Delta U from 3 to 4. Okay, here we go. Now what we just did was from 2 to 3. Here's your equation. And from 2 to 3, there you go. But if you want to go from 3 to 4, you're going to have to change these numbers. Okay. You're going to have to go 1236.4 minus 32. You're going to get a negative number from 3 to 4. Okay, let's do it. I'm getting a negative 335.8. Negative 335.8. Yeah, that's good. And last but not least, we're going to get the change in specific internal energy from 4 to 1. Okay, let's do that. We're going to go from 4 to 1 now. That means you got to go 520 minus 1236.4. Okay, here goes. 520 minus 1236.4. 2171. Did you get a negative 122.5? Negative 122.5. Yeah. Any comments or questions from anybody on any of that? All right. Okay, now let's use the first law and find out what this little w is. Well, you know how the first law goes. Here, let me write that. If you're happy now, nobody asked me anything. If you understood that, we're going to do the first law. And see, this is considered a what's the word? Control mass. CM, control mass. No mass gets out of this piston. No mass comes in. Now, in a real diesel engine, you do have air and diesel fluid coming in, and you do have exhaust gases going out. But we're modeling this instead of exploding diesel fluid with the oxygen in air. We're modeling this as a heat transfer in during ignition and a heat transfer out during exhaust. It's a thermodynamic model of the diesel cycle. And the first law goes like this. For control mass, And look, let's go from 1 to 2 now. From 1 to 2, we know delta U, and we know Q. Hey, here's an equation. We should be able to get the work from 1 to 2. I tell you what, it's either a plus or minus 205.8 BTUs per pound mass. And let me go to my friend. Well, all I want to know is, Roxana, all I want to know is, Roxana, is this work per mass positive or negative? You have a 50-50 chance to get this right. What do you think? Positive or negative? From 1 to 2. From 1 to 2, the work is positive or negative, Roxana? What do you think? She's thinking. Either that or she's on a coffee break.
Positive?
Did you say negative, Roxana?
Positive?
Oh, she said, oh no, she said positive. Oh no. Roxana, don't go to the casino. You had a 50-50 chance and you lost. Look, going from 1 to 2 is called compression. Roxana, what do you know about compression work? What do you know about compression work, Roxana?
It decreases.
I didn't quite hear you. I'm sorry.
It decreases.
Yeah, well, it's negative.
Yeah. Okay.
Yeah, you don't use the word decreases in regard to work. Work is not something that increases or decreases. Work is either positive or negative. See, work is not a property. Properties can increase. See, temperature can increase. Look, it went from 520 to 1723. That's an increase. But work doesn't increase or decrease. Work is not a property. It doesn't exist at a moment in time. But it's negative. And it's negative, Roxana, because it's compression. Going from 1 to 2, do you notice that the volume gets smaller? Look, the volume goes from here to here. In fact, it's 20 times smaller. So it's compressing. Compression work is negative. And Roxana, what do you think about expansion work? Expansion work is what?
Positive.
It's positive. That's correct. Okay. Well, since Roxana knows it's negative, we're going to put a negative on there. So we're doing great. And now we're going to fill in these other boxes. Oh, wait a minute. Auga. We don't know either one of those. However, I could fill this one in because we know what the delta U is from 3 to 4. And we know what the Q is from 3 to 4. We should be able to get the work per mass from 3 to 4. And I tell you what, it's either a plus or minus 335.8. Let me go to my friend Roxana one more time. Roxana, if you go from 3 to 4 and the volume's getting bigger, they call that expansion. What about the work, Roxana, plus or minus? Going from 3 to 4, is it plus or minus work per mass?
It's plus.
Say again, please.
Positive.
Positive, good going. Expansion work is positive. So you put a plus right there. See, you're expanding. You're doing work. See, that's called the power stroke on the diesel engine. Okay, well, we can do this one too here. See, this is what, from 4 to 1. So we can again go from 4 to 1, 4 to 1, 4 to 1, 4 to 1. And what's strange about this is there is no work per mass on that isochore because the piston doesn't move. And so to solve for the heat transfer, here I'll draw it for you. See, there's a heat transfer into your piston. Here they call that Q23. And there's a heat transfer out. It's at that hot exhaust, and that's Q41. And heat transfer out, you can see what the number is algebraically. It's either plus or minus 122.5. But we need to know whether it's plus or minus. Let's go to one of my other friends here. I just picked on Roxana. Parker, I want to know, is this heat transfer per mass positive or negative from 4 to 1? Parker's thinking.
Negative.
It's negative. Good going, Parker. It's negative. Now here's how it works. If the heat transfer is out of your system, if you're talking about the heat transfer, if it's out of your system, it's negative. If the heat transfer is into your system, it is positive. Do you see this heat transfer here? It's going into your system. It'll be positive. Now we never did do it though. We never did get the Q23, but we're going to get it now. But you need to know that. You need to know heat transfer is either plus or minus depending on whether it's going in or out. Okay, well, let's get this this heat transfer into your system. There is no heat transfer on these adiabats. See the zeros? Those are adiabats, so they don't give you any heat transfer. But I gave you a formula a long time ago. In fact, I derived this formula during our class. And the heat transfer per mass is equal to the change in specific enthalpy. But there's a catch. This only works for a particular kind of process. Let me go to my friend Parker. Parker, this is a lovely equation, but it only works for what kind of process, Parker?
Isentropic?
Nope. Guess again. I'll give you 3 guesses.
I'm not sure.
That's okay. That's what you're here for. You're going to learn what it is. Now, we've done this before, and I bet, Parker, you take excellent notes, don't you?
Sure.
That's the attitude. Yeah, I bet you got that in your notes. But the rest of you I know also take excellent notes. And you know this is a lovely equation, but Mr. Griffin has warned you about it. I have put the skull and crossbones on this. I know what my students do. They go ahead and they use these equations, whether they're good or not. You got to be careful with that equation. It only works for a particular kind of process. Let me ask somebody else. I bet somebody out there knows. I'm always picking on Stuart. Stuart, tell the group when you can use this equation. Earth calling Stuart, Earth calling Stuart. Come in, Stuart. Uh-oh, I think Stuart had to take a break. We'll go to my friend Spencer. Spencer, this is a lovely equation. I've warned you about it. It only works for what kind of process?
Isobars.
That's it. It only works for isobars. Now, I derived this equation for you guys. And the interesting thing about it is it doesn't even have to be an ideal gas. Now, we have an ideal gas, but that equation is good whether it's an ideal gas or not. But like Spencer just told us, it's got to be an isobar. Well, we have an isobar. Look, going from 2 to 3 is an isobar. See it? The pressure stays the same, doesn't it? So we can do it. And we have a lovely equation for this. It goes like this. Now we're dealing with English units. So you have to go digging around to find what this is in English units. I think this is 0.24 BTUs per pound mass Rankine. But just to be sure, maybe I better check. Now the temperatures going from 2 to 3 are 3,200 minus 1723.5 Rankine. But let me double check. I don't want to lie to you guys. If you go to the back and you look up C sub P for air, C sub P for air. I'm trying to find it here. By Jove, it's 0.240 BTUs per pound mass Rankine. I got that right. See, even a blind squirrel finds a nut now and then. All right, do that for me. Let's go. Well, I got an answer. I wonder if I did it right. Did you get a positive 354, 354.4? I'm going to round it off to 354.4.
That's what I got.
Yay! Now here's one way we can check our work. If we add these up and you add those up, wait a minute, Auga. We don't have that one, do we? Well, we can get it. Here, let's get it. Is there any question on any of that before we get this work going from 2 to 3? I guess there's no question. So I'm going to erase this. We're going to find the work from 2 to 3. if you're happy. All right. Okay, from 2 to 3, the first law says, and see, we know this, and we know that we should be able to get that, algebra students. I'm going to do it. You guys all took algebra. I know you can do this. Solve it and get the work there. Here goes. I'm plugging this stuff in now. Well, I got an answer. I wonder if it's the answer I got before. Slightly different answer, but maybe I did something different. I don't know. I'll try this again. Now, if people are coming up with slightly different stuff now, you tell me, please, because I'm quite capable of pushing the wrong buttons here.
That's what I got.
I bet that's right. Okay, now we're going to add these up because, see, in a cycle, the sum of the Q's should equal the sum of the W's in a cycle. All right, well, I'm going to add those up and see what I get. Here goes. I'm getting 231.9. Now I'm going to add these up. Well, something bad happened. I'm getting, let me try that again. Maybe I made a mistake. Nope, I'm getting 231.9 when I add those up. Good, excellent. We have filled in our table. Now let's answer whatever the question, whatever else they wanted. Says here, find the cutoff ratio, expansion ratio, exhaust temperature. Well, the exhaust temperature, we got that. That's the 1236.4. Here, let's put those isotherms in there. At state 4, we have 1236. Kind of messy, but that's the 1236. Can you read my writing? 1236. A little bit messy there. And then state 2, we have the 17. Wait a minute, I did that wrong. State 2 is 17. I'm going to have to do some fudging here. No, that's right. No, that's not right. 17 is bigger than 1236. The 17 we're going to go through here. That's the 17, 23. That goes through state 2. See, it's 1723. And then what is this 1236? Well, that goes through state. I'm getting all fouled up. No, wait a minute. No. State 4 is 1236. I'll get this right eventually. I think it does this. Sorry to be so dang messy here. Now that's state 4. See, this bottom one is 520. The one going through state 4 is the 1236. And then you have state 2, which is 1735, right? State 4 is 1236. Guys, I'm getting confused on my isotherms there. We're going to get it right, though. 520. Yeah, I've got all these numbers are correct. I'm just having trouble drawing these isotherms. Now, the hottest isotherm is the 3200. You guys can see that. The next hottest goes through state 2. It doesn't go through state 4. The coolest one is 520, but the next coolest is it goes through state 4. Yeah. All right. Here's state 4. State 4 is the 1236. And no, that's still not right. The hottest is the 3200. Okay, I got that. The coolest is the 520. I understand that. Now the next hottest is which one is the next hottest? Well, it's the 1723, isn't it? That goes through state 2. It's the 1723. Sorry to be so messy here. You probably can't read this anyway, it's so messy. State 2 is hotter than state 4. Okay, well, that must mean that it does this. And state 4 has to do this. There's T2. This one would be T4, right? T4 is the 1236. And T2 is the 1723. Well, I think we finally got that. Now they wanted something about something else. I don't know if they wanted the efficiency, but let's do that. We've got about 10 minutes before our break. If you wanted the efficiency, that's going to be your 231.9 divided by this. This costs you money. See that 354? There's this heat transfer in. You gotta go buy gas at the gas station. So that's the 354.4. So we can get the efficiency. Here we go. 231.9, 354.4. I'm getting 0.65, 4, 3, 65% efficient. You're not going to get that with a real life diesel engine. This is an ideal diesel engine, no friction whatsoever. Okay, so we did that. And now they also wanted something else. Let me read it here. The cutoff ratio. Well, the cutoff ratio, I don't think they ever gave us that. Did they? Oh, they gave us the compression ratio. This thing called, that was 20. They gave us the compression ratio, but they also have something called the cutoff ratio. And what that is, the cutoff ratio is V4 over V3. Here's V4, there's V3. They have a fancy name for that. It's called the cutoff ratio, and we got them. You just plug them in. Let's see what it is. V4 is 1388. V3 is 1.288. I'm getting 10.8 cutoff ratio. And then they said the expansion ratio. I guess there's 3 different kind of ratios with the diesel engine. The expansion ratio is, I think it's V3 over V2. No, it's V4 over, okay, no. This is wrong. I'm sorry. The V4 over V3 is called the expansion ratio. I got those backwards. Unless you're designing diesel engines someday, I'm not going to ask you this on a exam, but they exist. They have another thing called the cutoff ratio. The cutoff ratio is the V3 over V2. If you want to know what that is, it is well, I'm getting 1.86. Wonder if that's what I got when I did this before. V3 over V2 Yeah, that's what I got. And yeah, those are correct. And we have just conquered that was good. That was good for us. We needed to know to review the English, the British engineering stuff with BTUs, and hey, you found out what a BTU was. That's good. All right. Now we're going to take a 10-minute break, and we're going to have some of this will be a review, which will be good. But I also want to explore a topic that we haven't talked about. So I want you guys to go take a 10-minute break. Go stretch. We'll be back. I've got, I don't know, 10 to 10. So at 10 o'clock, we'll have more fun. All right, go stretch. We'll be back. Go stretch. Okay, we'll be back. 10-minute break. Well, just about time is up here on this 10-minute break. I keep forgetting to do a TS diagram. Why don't we real quick just do a TS diagram? You need to know how to do TS diagrams for sure. Here, let's do one. Won't hurt anything. Now again, there's no vapor dome because we're dealing with air and it's not going to liquefy. So don't put a vapor dome if you're dealing with air. Now, it's got two isentropes. Well, isentropes go straight up and down. That's constant entropy. See, when delta S is 0, they call that an isentrope. Well, delta S is 0 from 1 to 2 and 3 to 4. Okay. Now, what does the temperature do? Well, the temperature goes straight up, looks like, from what, 520 to 920? Here, we'll put some, no, that's not right. From 520 to 1723.5 Rankine. From 5, yeah, there we go. There's state 1, there's state 2, and we went straight up. And then you have an isobar. Isobar. Now, I've told you about isobars on a TS diagram. I think they kind of go like that. So I need some room here. I'm going to fudge here a little bit. We'll put the 720, 1723, 1723 down here a little bit. I needed the room. We won't put it up quite so high. But see, isobars kind of go like this. They go like that. So there's state 2. And there's state 3. And see, it's real hot. State 3 is 3200. So it would be right here, 3200. And then, well, you got to go straight down again. To state 4. And then what's 4 to 1? Oh, no, wait a minute. Yeah, 3 to 4 is straight down because it's an isentrope. And 4 to 1 is an isobar. Now, isochore. 4 to 1 is an isochore, and they're steeper. There's your isochore from 4 to 1. Kind of looks like that. See, this one's an isochore, and they are steeper than isobars. This one's an isobar. These two are isentropes. And so you could put your temperature at 4. What's the temperature at 4? There you go. It's 1236.4 Rankine. There you go. Got all the temperatures on there now. That's good. Now, what about the pressures? Well, see, this pressure here is constant. From 2 to 3 that has the same pressure. It's 920 psi. Yeah, you could put the pressures on there. I don't know if we put the pressures on here. What is the pressure at 4? It's 33. No. Yeah, that's right. The pressure at 4 is 33, and the pressure at 1 is, well, it's 33.88. Pressure at 1 is 13. Now, wait a minute. The pressure at 4 is, that's not right. Did I make a mistake? No, that's right. It's not 33 point. It's 33.0 at 4, not 88. It's 33.0. Here it's at 13.88. There you go. At 1, and that's at 4, 33.0. No, we did it right. Okay, we did a TS diagram, and we're pretty happy with that. And let's move on. We're going to have a little bit of a review here, and I'm going to erase this whole thing here unless you have a comment or question. Well, okay, no, I didn't hear anybody, so we're going to erase this whole thing. And we've done diesel cycles with English, and we've done it with metric. Now I'm going to try something I haven't done with you guys. I'm a little bit afraid to try this. I'm not very good at this computer stuff, but my IT person, my daughter, tells me I can share screen. I'm going to try it. I'm going to share screen, and I'm going to try to. I'm going to try my best to give you guys a little talk that partly review here. But what I'm going to do is plug in this, what do you call it? I can't think of the name of it. There, I plugged it in. There we go. Now I have to click on the one I want. Okay, now just a minute now. Bear with me. I forgot the name of my file. I forgot the name of my file. Doggone it. There's a zillion files on here. All right. Let me keep trying. Yeah, I remember now. Okay, I haven't given up yet. I don't know if you guys can hear me. Can anybody hear me talking? I might have lost everybody.
I can hear you.
Oh, good, good. I'm looking for my file here, and just bear with me and have patience. I appreciate it so much. I know the name of my file. I just have to find. I've got a zillion files here. Okay, let me keep looking here. There it is. I found what I wanted. Now I'm going to click on that. And my daughter told me I need to click on Zoom right away. There. A pop-up will come at the bottom and you will need to select the Share to Everyone tab. Oh, I forgot to do that. Share to Everyone tab. Oh, gee. I might have lost everybody. Oh, gosh. I don't know if I can get you guys back or not. Hey, hey, can you guys see that?
I can't yet.
I forgot to click on something that says share with everybody. That might be where I fouled up, but you can hear me.
Yes.
Yeah, we can hear you and we can still see you in the whiteboard.
I don't want you to see me. I want you to see what I. Okay. Well, maybe I might have to reboot you guys all up to start with, because I forgot to click on Share to Everyone tab, and my daughter's at work. She can't help me. Share to everyone. I don't see anything that says share to everyone.
If you go into Zoom, there should be at the bottom middle like a green share screen button.
Yeah, now that's what I clicked on. I clicked on that. Okay, well, let me, yeah, now you guys can see me again, right?
Yes.
Good. Okay, now I'm going to follow her directions now. I'm going to click on the share, little green share screen thing. Okay, click. Now what? I haven't seen this. I haven't seen this screen before. But it says share. Oh, gee. You are screen sharing, it says. Participant security, stop video, mute. No, I'm trying to share. I'm trying to share something. I might have to write it out, guys, the way things are looking. At least I tried. I tried something new. I was worried about it.
I can
Right
see your-
now, yeah, we can see your screen. We can see you're on the Zoom website.
Okay.
So
But I
if you
wanted-
change whatever you're looking at to whatever you want to show us, we might be able to see it.
Okay, now to get it, I have to go to my files. And to go to my files, don't I have to go to, my daughter says go to Google. That's not Google. Okay, well, I think I'm going to give up and just write this out for you guys. Stop share. Hey, are we back? Can you
Yes.
hear me? You guys can hear me. Okay. Well, never mind the screen share. Obviously, I don't know how to do it, but I can show you the old-fashioned way what I wanted to show you. Be nice if I had this written out nicely for you. I just had it on my screen. I might have to do it from memory. I don't know. Okay, well, we'll just do the best we know how. I don't know what else to do. But when you do problems, there's a step-by-step method for solving problems. You all know that. And here are some, we've gone through this before, but you have to decide whether it's a control mass or a control volume. You got to decide that. Because the first and second laws are different. Like for control mass, it goes like this. Or in little letters, you could write it like this. Well, no, these would also be big letters. But that's the first law for control masses. I want to make sure everybody's on board here. I wanted to share screen and I have all this on a file, but obviously I didn't know how to do it. But we still have a few of our excellent students that are still tuned in. Aubrey, are you with us? Can you see on the? Can you see that okay, Aubrey?
Yeah, I can see that.
Oh, okay. Now see, if these terms here are negligible, then you can just get rid of those big letters. Ta-da, there you go. Now that's for control mass. Now for control volume, well, you know how that goes. Oh, gee, I won't have room for this because it's so long. Let me scoot it over here. Now, all this was on my file that I wanted to show you guys, but I wasn't able to figure it out. If I had my daughter here, we could do it. Uh-oh, see, I ran out of room. Now that's the first law of thermodynamics for control volume. You've got to decide, is it a control mass or a control volume? I hope you all understand the difference. That those problems we just worked with the diesel cycle, those were all control volume. So you have to use this equation here. Okay. No, I just lied to you. I just lied to you. The diesel cycles were control mass. So you have to use this equation here. There we go. Good. And then there's the second law. See, all this stuff is the first law. But there's also the second law. Now for a control mass, it goes like this. I'm doing this from memory because I couldn't find my file there. But I think that's right. I think Now wait a minute. Now wait a minute. No, 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 no. No, 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 no. No. There. There. Now that's right. That's right. Now in little letters, it goes like this. There's your second law for control mass. We've had all this before. It's in your book. I could show you the page numbers. But now for control volume, it's a little different. It goes like this. I tell you what I'll do. I'll put, I know how to get that file that I wanted to show you on content. I'll put it on content. That way you can, all of this stuff that I'm doing right here, you can see it on content. And that'd be nice for you to have.
Is this the step-by-step to solve thermo problems document you're talking about?
Yes. Do I
That's
have
already on the content. That's posted on content this morning.
Oh, good. I've already put it on content. This is called, the file is step by step to solve thermal problems. Yeah. And then the second part of it, well, first of all, is the step by step. And then the second part of it is all of these first and second laws. And so I'm so glad that you have that. That's on content. Thank you so much. I think I got that right. But so we've got it for control masses, control volumes, first law, second law. And what I never did show you guys is for transient processes. I need to write for you the transient processes. Now they are a form of control volume problems, or where you have a control volume system. See, this is the one you'd use if you had a steady state. That's zero, it makes it nice. But not everything is a steady state. When you start up a turbine, for example, it's not steady state. It starts from zero pressure up to a high pressure, and it takes time to do it, maybe a few minutes to crank up. And so when it's starting up, it's called a transient equation. And so let me see if I can write that for you. I'm so glad you have all that. I'm going to erase all this because we've had it all before. This is kind of a review, but what is not a review is the transient process. We're going to talk about the transient process. And it goes like this. And what this is this is the first law. There's a first law and a second law for the transient process. It's when you start up something like a turbine, for example. It gets kind of long. let me find this one in the book. Let me show you where this is in the book. That might be good. It's in chapter 4. And it's called the transient process. Yeah, there we go. In my book, it's on page 131. And the actual equation's on page 132. And they have this right here, what that is E2 minus E1. That's the total energy in your control volume. This is a control volume thing. And this is the final total energy in your control volume. And this is the initial total energy in your control volume. And you'll see that. I see it on page 132. There it is. And then the rest of the equations down at the bottom of the page. Now they put a little CV down here, but that's really not necessary. We know it's a control volume. And there it is. That equation is on page 132. And I want you to know the difference between these 2's and these 1's. And these I's and these E's. See those I's? M-I-H-I, V-I, Z-I, M-E-H-E, blah, 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 blah. 2 stands for final. 2 stands for final. 1 stands for initial. But I and E stand for something else. Here, let me ask one of my excellent students. Stuart, I'm always picking on you. What does the I and the E stand for in this equation? We've seen them before, Stuart. We've seen I's and E's before. What do they stand for?
I don't quite recall right now.
I love honest answers like that, Stuart. I stands for incoming, and E stands for exiting. That's a totally different idea than final and initial. See, this stuff here is coming in. That's an incoming mass that's coming into your turbine, maybe, or your pipeline, or your boiler, or your throttle, or your nozzle, or your heat exchanger. It's incoming, and the E is exiting, it's leaving. Whereas the 2 and the 1, that's what you got inside your system. At the end of the process, and the 1 is at the beginning of the process. Well, this is the transient form of the first law. There it is. The transient form for the second law, I might be able to get it from memory. It's in chapter 7. See, this is in chapter 4. In chapter 7, I wanted to do something else. You guys can read that on that step-by-step on content. And what was I going to do? I got lost here. Oh, I was going to tell you that this right here is what I call the granddaddy of all the first laws. All the other first laws can be derived from this one. For instance, if you have a control mass, well, then you don't have any incoming or any exiting. If you have a control mass, these terms are zero. There is no incoming mass, and there is no exiting mass, so those terms go bye-bye. And you know what all this is? This is just a big fancy, it's just a big fancy name for your final total energy. And all this is a big fancy name for your initial total energy. So you wind up with E2 minus E1 equals Q minus W. It's no longer a control volume though, it's a control mass because we got rid of the incoming and exiting terms. So this fancy big equation reduces down to the first law for control masses. I call this the granddaddy of all the first laws. And the same sort of concept could be applied to the second law. You can also get the first law for control volume from this granddaddy equation by dividing through by time and making the time exceedingly small. And what you'll wind up there, see, if you divide this through by time and make the time approach zero, then you'll have dE dt on the left side of the equal sign. And on the right-hand side, well, I think you can see it comes out to look like our first law that we know and love, that we've written many times before. I thought that was a good review to mention all of those, and you have them all now on content, all of your first law. You also have your step-by-step. Let's go over a few things from the step-by-step, and then I'd like to do a transient problem for you. Maybe that'll be good. We could use some of our principles. You've got to decide when you do a problem, is it SI or is it English? It sure makes a difference. If it's SI, you use the SI tables in the back of your book. If it's English, you use the English tables. Kind of makes sense. You don't want to get them mixed up. You have to decide whether it's a control mass or a control volume. That determines which first and second laws you use. I know there's some other things, but I can't think of them. My mind is sort of blank right now. I'll tell you, but you have to decide on some things when you do a problem. Now, the problem I want to do with you guys. Oh yeah, here's another thing. You have to decide, are you going to do a PV or a TS diagram? You know you need to do one or the other. For some problems, a TS diagram is very helpful. And you know some facts about this. Something to do with the area under a PV diagram and the area under a TS diagram. I bet you know this. Let me call on somebody and see if they remember what this is. Parker, unmute. And tell me something about the area under a PV diagram. What's that area, Parker?
Work per mass.
Yay, good going. Excellent. As long as I've got Parker on the line. Parker, what's the area under a TS diagram?
Specific heat transfer.
That's it. Very good. That's why that's so important, because it gives you the heat transfer. This gives you the work. Yeah, great. But I want to show you something I don't think I ever quite explained. If you have a control mass, the area under a PV diagram is the work, yeah, or the work per mass. But if you have a control volume, let me show you that. If you have a control volume and you have a process, let's say you go from 1 to 2 here. It's not the area under it this way that gives you the work. It's the area this way. This gives you the work per mass. If you have a control volume, the area under the graph is still the work, but it's this area sideways. That's in your book. Those of you that have read the book, there's a lovely explanation of that in here. I wonder if I could find it. I don't know if I can find it or not, but I'm trying. I'm trying to find that. Maybe I'll get lucky and find it. If you know where it is, let me know. I'm having trouble. Okay, let me keep, I'm not quite ready to give up. Yeah, here it is. In your book, if you look on page 218, you'll see a process. Well, they've got it going in a different direction, but it really doesn't matter. They've got it going from 1 to 2. Here, let me draw it the way they have theirs. They have a process doing this from 1 to 2. And here's the area underneath the area, but it's the area sideways. This is the work per mass if you have a control volume. If you got a control volume, that's the work per mass. It's sideways. It turns out that the little w is equal to the integral of VdP. See, what you guys are used to is the integral of PdV. That's what you have with a control mass. But if you have a control volume, this is explained in this chapter 7. And you'll find this equation on page 217, only I forgot the minus sign. Let me talk about that equation a minute, and then I'd love to work a problem. This is an equation on page 217, and they said the work per mass done on a control volume is equal to the integral of VdP. It's not PdV, it's VdP, only there's a negative. Now, let me show you why that is. Specific volume is always positive. You can't have a negative specific volume. Have you ever heard of anybody that has a negative volume? I don't think so. We all occupy a positive volume, and so our specific volume is always positive. So that's positive. However, the pressure kind of depends on your process. Now, if the pressure increases, then it would be plus. The change in pressure, if it's increasing, in other words, if you have compression, the pressure is increasing. And so you have two pluses. The minus tells you that the work is negative if you have compression. See, this is what would happen if you had compression. Now, if you have a control volume, the specific volume is always plus, but you could have a negative change in pressure. How would you do that? Maybe take some weight off and it expands. You've got expansion now. See, if the change in pressure is negative, you've got expansion. And the algebra says you've got a positive times a negative, which is a negative, but you have a negative in the equation. That gives you a positive. So you get positive work per mass for expansion, and you get negative work per mass for compression. Okay, well, I told you that. I want to take our time left and work a problem with you. And this is problem number 483. Today is a little bit of a review day. Now, when we come back on Monday, I think what we're going to do Monday is the Stirling cycle. You can read ahead if you want. And we'll have fun working a Stirling cycle on Monday. Make a note of that. Monday, we will do the Stirling cycle. But right now, we're looking at 4.8. Let me find it. This is going back a few chapters. But that won't hurt us to review some stuff. So some of this is not really a review because to solve this problem, we have to use that transient equation. And I'm just giving that to you today. Okay, now let me find this. All right, here we go, 4.8. Is that the one I want? Just a minute. No, 483, sorry. What I want to show you guys is problem 483. All right, let me find it. .483. Well, it's a tank that's empty. It's a 2.5 liter empty tank. Here, I'm going to draw you a picture of a tank. There it is. Only I don't like liters. We're going to get cubic meters. Move your decimal over 3 places. And what you'll have is 0.0025 cubic meters. See, there's 1,000 liters in a cubic meter. We could have looked that up in the back. Okay, it's empty. It's state one, it's empty. So what would be the mass at state one if it's empty? We'll go to one of my wonderful students here. Spencer, if it's empty, what would be the mass inside of it?
0.
I like 0. It will be 0. Now, state 2, this is going to be state 2. Now, the thing is, though, see, they have this line coming in here. There's a line coming in, and there's a valve here. We're going to open that valve, and what happens is ammonia comes in. Open that valve, and it goes like that, and ammonia comes in. And they told us that there's 10 grams of ammonia. See, there's this line, and we open the valve. 10 grams comes in. And then I think what happens is you shut the valve off. We're going to shut the valve off. Okay, so here it goes. You ready? There, we shut it off. And now you have 10 grams of ammonia inside. And it says here, the ammonia comes in at 25 Celsius. And it's saturated vapor. Okay, well here, let's write the properties. Now there's no properties here. I mean, the pressure at state 1 is 0. There's nothing in there. But we could write the incoming pressure, the incoming temperature, the incoming specific volume, incoming specific enthalpy. I don't know if we need the incoming specific entropy, but we can write it all down. Let's do it. Now, to do that, we need to go to our ammonia table. Help me find the ammonia table. I'm digging through the ammonia table. Can you find the ammonia table? Now, they said coming in, it's saturated vapor. Saturated vapor ammonia. All right, well, let's see. See, this, in a way, this is kind of a review. Saturated vapor, you should be able to look these up. At 25 Celsius, coming in at saturated vapor, I get 0.12813. 0.12813 cubic meters per kilogram. See if you can find that. Now, I might need this little h, so I'm going to get that. Now, that's 1463.5. 1460. See, this is easy, really. And that, what is that? Kilojoules per kilogram. I don't know if we need this S, but we'll get it. 50293. 5.0293 kilojoules per kilogram Kelvin. What about the temperature? Well, that's 25 Celsius. What about the pressure? Well, I don't know. What does it say? Let me ask somebody out there, see if anybody's following along or if you're just letting me do all the work. Oh, I've lost some of my students, but I have a few diehards that haven't given up on me. Parker, proud of you. You're still with me. What's the pressure of the incoming ammonia, Parker?
0?
No, no, the pressure is 0 of what you got inside here at the beginning, but we have a line here and we're going to open that valve, and in that line is ammonia, saturated vapor ammonia at 25 Celsius. What's the pressure? You'll have to go to your, Parker, you'll have to go to your table. Can you get to that table pretty easily?
Just so everybody knows, I'm looking at the table B.2.1, and in our version of the book, the online version, they messed up the headings
Oh, yeah.
for the volume, for the V and the U. They printed it as H and S again.
They got them backwards, didn't they, somehow?
Well, no, it's just H and S appear twice, but the numbers are completely different because one of them is actually H and S, the other is V and U.
But the pressure, they should have the pressure on there.
Yeah, the pressure's right, but just for everybody else who's looking for the other stuff.
Yeah, thanks for telling us that. Because they've mislabeled the column headings. But what's the pressure at 25 Celsius?
1003.2 kilopascals.
You're absolutely right. 1003.2 kilopascals. Good going, Parker. Thanks for that other information. Isn't that awful? You pay your good money for this stuff, and they mislabel the columns. Okay, now let's go. That's all very, very well and good, but let's go to state 2 there. Now, this isn't going to change. This line is going to stay at 25 Celsius, and it's going to have the saturated vapor coming in. Nothing changes there, but now we're going to go to state 2. Okay. State 2 now. The mass at state 2 is, well, you'd have to put it in kilograms. It'd be 0.010 kilograms. So you take 10 grams and you move it over 3 spaces, right? That's the mass. Now to get the specific volume, what you do is you take the volume and you divide by the mass. Well, what's the volume? Well, they gave you that. It's 0.0025. Let me write that down. 0.0025 cubic meters, and the mass is 0.010 kilograms. Hey, we can get the specific volume at state 2. Right? Somebody do that and tell me what you get for the specific volume at state 2.
.25 meters cubed per kilogram.
That's what I get. 0.25 cubic meters per kilogram. Now we never did the specific volume at state 1, but we could try. See, at state 1, what you have is 0.0025 cubic meters divided by the mass, which is 0. Hey, wait a minute, we're not supposed to divide by 0. So make it something exceedingly small, okay? Like maybe 1 times 10 to the minus 10 kilograms. That's close to 0. So what do you get for your answer? Well, it balloons to infinity, doesn't it? The specific volume at state 1. Now, to be honest about it, there might be a stray molecule or two inside here. it's hard to get a perfect vacuum. But essentially the mass approaches zero. So this denominator approaches zero, specific volume approaches infinity. So that's all well and good. We did good. Now, do we know anything else at state 2? Let me read this again here. We're doing problem 483, and it says, the ammonia comes from a line, we read that. We cool the tank while we fill it, keeping its content at 30 degrees Celsius. Okay, now what they're going to do is, as they fill it, got a red pencil around here someplace. You know what happens when you fill a tank? It gets hot. I don't know if any of you do scuba diving, but when they fill those tanks up, they get hot. You have to let them cool off. And what they're going to do is they're going to have a heat transfer out as they're filling it up, and they're going to keep the temperature at a constant 30 degrees Celsius. So we know T2 is 30 degrees Celsius. They're going to keep the temperature at 30 degrees Celsius. Okay, great. Well, we got a lot of information now. We've drawn our device sketch. We've calculated some wonderful stuff here. What we need is a PV diagram and our first law, and we'll solve the problem. Remember, to solve problems in this class, there's a method. There's a step-by-step method, which is, I gave it on content for you. You draw the device sketch. You draw the PV diagram. Now here, let me draw it for you. Okay, here we go. I just need some room here someplace. Yeah, I hate to erase all that, but we desperately need the room. Okay, PV diagram. Now this ammonia does have a vapor dome. It's ammonia. It does have a vapor dome. Now the ammonia is coming in as saturated vapor at, what did they say, 25? Well, let's draw the 25. You're right there at state. Well, that's your incoming state. It's not state 1. It's your incoming state. Now, the pressure is 0 at state 1. So that means you're on this 0 axis here for pressure. Here's your pressure. So you're on this 0 axis someplace. Now the specific volume at state 1 is essentially infinity. So I ran out of board. Strangely enough, state 1 is way the heck out here. The incoming state is right there. But where is state 2? Well, I don't know. It's at 30 degrees. Let me fudge this just a little bit. This slopes downward a little bit more than that, kind of like that. It's going to end up at 30 degrees. Now, 30 degrees kind of does this, sort of follows along like that, comes over here, and then that's your 30 degrees Celsius. You've got to learn how to make PV diagrams. But where, there's state 1, but where is state 2? Well, it's somewhere on this 30-degree line. What else do we know about state 2? Well, we know the specific volume. Tell you what, let's go shopping in the tables and we'll find out exactly where state 2 is. It's going to be in superheated vapor. And if you go to your superheated vapor at 30 degrees, here we'll make a little table down here. I just need some room. I don't think I need that. At 30 degrees Celsius and 500 kilopascals, the specific volume is 0.28103. And at 600 kilopascals, at 30 degrees, the specific volume is 0.23152. But see, what we want is 0.25. We know the specific volume at state 2 is 0.25. So we can find the pressure by interpolating between 500 and 600. We know it's between 500 and 600 because 0.25 is between 0.28 and 0.23. Now here's your chance. Some of this is review. This is review from day 1. Remember when we taught you how to interpolate? I'm going to shut up for 2 minutes. We got time. And I want you to find the pressure. We know state 2 is somewhere along this 30-degree line. I can even tell you where that pressure is there. On 30-degree line, the pressure is 1167. This is 1167. But that's not what our pressure that we want. We're going to find it. I'm going to shut up for 2 minutes and I'm going to interpolate. I want you to interpolate and I want you to find this pressure. Let's see if you can do it. Go for it. Well, I got an answer. I wonder if mine is right. Any of you guys coming up with an answer? I'm not sure mine's right. Spencer, did you get an answer right here, Spencer?
I got 537.33 kilopascals.
That's not what
I
I
made-
got. It's not what I got. Well, what about Parker? What'd you get, Parker?
I got 562.67.
You know what? That might be right. I got something slightly different. Let me do mine again. But I bet you're right. That sounds right. Yeah, you know what it is? It's 562.7 kilopascals. It's kind of down here someplace. Now here's state one, and here's state two, and here's your process. It's kind of weird. I know it's kind of weird, but there it is. You went from 1, way out there at infinity, to 2, and the pressure at 2 is 562.7. 562.7 kilopascals, and that is that's the correct answer. We have just got the correct answer. This is the incoming ammonia. This is the initial ammonia. Well, there isn't any. There's no ammonia in there, but the specific volume is way the heck out there in infinity, and the pressure is 0. There's your ammonia at state 2. It's 30 degrees, and the pressure is 562.7. So we did good on that. Now let's see what they wanted us to do. They wanted us to do something else. We've got 13 minutes. Let's answer their question. This was problem, oh gee, I got lost. We're doing 483, guys. For those of us that are still with me, that's what we're trying to do. We're trying to do problem 483. And I lost my page here. Okay, 483. Yeah, there it is. Find the final pressure. That is correct. We got the final pressure. It's 562.7 kilopascals. And the heat transfer. They want see, there's a heat transfer. I drew it for you. Remember these, when you fill these tanks, they get hot. And they're cooling them off and having a heat transfer. And we can do it. But to do it, we need the, see, these are the specific volumes here. We need the internal energies. So help me go back and find the internal energies at 30 degrees and at 500 kilopascals and 30 degrees Celsius. We're going to need this. It's 1373.0, and here it's 1368.2. These are from the tables. This is table B.2.2. And we have to solve that. We got 10 minutes left in class. We need that U2. We need to interpolate and get the U2. Well, we can do it, can't we? Yeah, we can do it. Here goes. I'm gonna interpolate that now and get the answer. You know what it is? It's 1376. Okay, now we can solve the problem and find the heat transfer. Here we go. I just need a little room. Now let's see, we've done our PV diagram. And what we haven't done is our first law of thermodynamics. But there's some room right here. The only thing is you can't use the control mass or the control volume form. You have to use this form here. Now I know there's some other terms there, but this tank is not moving, so there's no kinetic terms. And it's not going up and down, so there's no potential terms. Now there is a heat transfer, but there is no work. There's an incoming, but there's no exiting. Guys, we can get rid of this term here. Now let me ask somebody why we're down to three students are still with me, and we have 8 minutes. So I'm always picking on Stuart. I'm proud of you guys for sticking with me. Stuart, how come the mass at state 1 times the specific internal energy at state 1 is 0? How come, Stuart? Why is that 0?
The mass at state 1 is 0?
Yeah, they don't have any mass at state 1. Good going. Now, back to Stuart. There's no work done when you open the valve and put some ammonia in this tank. There's no work done. There's no spinning of turbine blades or lifting a weight. And finally, Stuart, the exiting mass times the exiting specific enthalpy is 0. Why is that term 0, Stuart? How much exiting mass is there on this tank when you're filling it?
None.
There's none. There is no exiting mass. This term drops out. So what we're left with is M2. Now, M2 is 0.01 kilograms. U2, that's what this is. This is 1376. We had to interpolate it. 1376 kilojoules per kilogram equals Q. This is what they wanted. Plus, need a little room here. MI, well, MI is 0.01 kilograms. That's what came in. And HI, oh, there it is. We wrote it down. It's 1463.5 kilojoules per kilogram. Hey, look, we have a nice equation. Now, this equation is different than what you've had before. It's the, what do they call that? It's the transient process equation. We have 5 whole minutes. Go ahead and plug that in, and let's see if we can get the answer that I got when I did this before. We're solving for the heat transfer. It should come out to be negative because we're removing heat energy. We're transferring it out. Otherwise, it would heat up, right? When you fill a tank, it should get hot. So here we go. I'm doing it now. You do it. I got a negative. I got a negative 0.875. How about you guys? 0.875. I wonder if that's what I got before.
What I got just now.
Yeah, I bet that's right. Now we need to know the units on that. That's 0.875, but what are the units? Without units, we're in trouble. We have to have units. What do you think?
Wouldn't it just be kilojoules?
Yeah, good going. It's just plain old kilojoules. There you have it. We have a heat transfer out. We've done the PV diagram. Pull up that review stuff on step-by-step that I put on content, because we do that on every problem. And then I listed all of the first and second laws for your reference. It's all in the book, and we've studied them in class, but it didn't hurt to spell them out for you. There they are, first and second laws for control mass, control volume, steady state, and a control volume when you have the, what do they call this? I forgot already. My mind just went blank. That happens to you sometimes when I ask you guys questions. What's the name of this kind of process, guys? Help me. The name of this kind of process is the transient process. Okay. Well, we had a lot of fun, and we reviewed, and you got that reference material and content to study, and you're going to study about the Stirling cycle. We'll talk about that Monday. And I think you have some homework to do for me. So do your homework. Our time, it's sad, but our time has come to an end today. Here's your last chance to ask any questions. I'm going to push this little red button here. 5, 4, 3, 2, 1. Nobody said anything. Okay, well, bye-bye for now. I'll see you on Monday. And all of this is on, it'll be on YouTube.